power of recursive algorithms. Actually, this problem, this example, I think you learned already from the CS3250. So I remember when I taught that class, I did this example. Yeah. So let's look at it again. So mainly, we look at first, think about if you do not use recursive algorithm, how hard it is. So I don't think I can do it without using recursive algorithm. So that's why we see the power of recursive algorithm. Second, we do analysis. Because in our 2250, we cannot do analysis. So definitely we cannot do analysis. But we learned a little bit recursion in that class. You know. I think first, you're familiar with this problem. It's a very famous problem, solving this puzzle. Yeah. So we are given 3 disks. Yeah. So the problem size 3, so not very hard. So you can do it. You know, after several tries, you can do it. So the rules, only 1 disk can be moved at a time. Okay? Yeah. Number 2, a disk cannot be placed on top of a smaller disk. Yeah. Yeah. You have to follow that order. Yeah. 3, all disks must be stored on a peg except while being moved. Yeah. So you have to keep the same stack like this in a different peg. Yeah. That's the rule. Okay. And for this problem, we want to solve a general problem for n disks, not just 3. Okay? So although the picture, we see 3 here, but our problem we need to solve for any number n. Yeah. Not just 3. Okay? So you can see it is harder, much harder. Yeah. When n, especially when the n is large, how hard it is. Okay? Yeah. Analysis. The larger the size, the harder the problem. Yeah. So we always use this simple fact. Yeah. This fact tells us we should work on relatively smaller size, problem size. Then it's easy. Yeah. So if we can solve a few easy cases, then we may get some idea for harder, more general case. Yeah. Let's try n equals 1 or 2, the simplest possible 2 cases. N equals 1, that's trivial. Right? Trivial. Yeah. How about n equals 2? Also pretty easy, right? Yeah. Okay. That's our base cases. When we do recursion, we need to have base cases. Right? So we have the base cases, 2 base cases. Okay? Yeah. All right. But now let's go, increase the size number. Let's do this kind of thinking. Okay. When we solve the problem of size 3, now let's go to 3 first. Okay. We can assume that we have already solved the problems of size 2. We can assume that. Okay? Yeah. So after we solve them, but definitely we can assume them. Right? All right. If you can assume that, do you feel the problem's a little easier? Right? If you can assume. Size 2 problem already solved. Okay? How about we fix the bottom disk? Okay? Can we solve size 2 first? After we solve size 2, can we move the bottom disk to another peg and do another size 2 problem? Right? You move it on top of it. So do another size 2 problem. Yeah. So things like that. You can see if you can assume the problem of smaller size, 1 size smaller, just one disk smaller, size smaller. Then from there, the problem looks much easier. That's the recursion. That gives us the recursion idea. Okay? Yeah. All right. So now, let's try to, using experiment, moving 3 disks and try to give us recursion, solution. Okay? All right. Original, we start at the beginning. We start from this case. Okay? First, top disk move to peg 3. Okay? Yeah. Second, the middle one move to peg 2. Okay? Yeah. Then move the smallest back to peg 2. Okay? So we solve, you can see, we solve problem of size 2. Then move the largest to peg 3. Okay? Yeah. And smallest to peg 1. Middle one to peg 3. And smallest to peg 3. We get a solution. See? Yeah. So from this experiment, so we try to get some rule. Yeah. Otherwise, we cannot go very far. Think about, if we go to 4 disks, it's too hard. 4 disks, you can think about. Okay, so we don't want to do that experiment. Yeah. So how do we generalize the solution to n disks? Yeah, n disks pretty much like this, but we want to make our view more general here. Okay? So here you can see after we do so many steps, we get a P2 solution. Right? Yeah. Problem size 2. P2 solution. We get a P2 solution. Okay? Yeah. P2 solution. After we get P2 solution, then we move the bottom disk. Then after that, we do another P2 solution. Can you see? Another P2 solution. Okay? Yeah. So that's the typical procedure. Yeah. Now the general case. Okay? So we extend it to the general case, n case. Okay? But here, without using recursion, you can think about how hard it is, especially for the general case, without using recursion. I cannot imagine anyone can do it without recursion. Okay? All right. All right, so we do problem size reduction. Okay? Yeah. Every time we only reduce the problem size by 1. Okay? Yeah. But we assume we can solve the problem of size n minus 1. Okay? Then we go from there. Okay? How much we need to do for size n? Okay? Yeah. All right, so that's our result. Okay? We still use this picture, but when we use this one, let's change our view a little bit, adjust our view. Let's treat this stack, there are n disks. Yeah, because it's hard to draw n disks. Yeah, let's still use this picture, but let's imagine we have n disks. Okay? We solve the problem of size n. Okay? So we need to solve the problem P of n, that function. Okay? That's the solution. Okay? Yeah. Assume we can solve P of n minus 1. We have that solution. So we just do the extra part. Yeah. So we do not do the whole thing. We just do the extra part. Okay? All right. Now, okay, let's solve P of n minus 1 first. Right? Yeah, n minus 1. That solution. We assume we have it. So let's do it. Okay? We have that solution. Okay? After that, let's move the bottom disk to an empty peg. Okay? Yeah. So that's easy. After that, let's solve another p of n minus 1. Yeah, another p of n minus 1. Okay? Yeah. So we get a solution. Yeah. Yeah. So here, so let's put some, the position. So based on their position, so let's put some notation. Okay? From peg, yeah. So we start our starting point from this state to our destination. So now we want to move destination, temp, yeah. So we need to use it as a, temporary manipulation peg. Okay, all right. So based on this, thinking, let's look at the implementation of recursive solution. Move disks. Number of disks, first parameter, but you also need to specify 3 positions for your 3 pegs. Okay. Yeah, because their location or their symbols important here. Okay. Now, look at this. Okay. All right. This solution corresponds to this function call. Move disks, the disk size from peg to and the temporary. Yeah. So the solution corresponds to this function call. Okay. But this function call, we need to do recursion. Okay. Yeah. All right. So now we need to do this. Okay. We need to solve this problem. Okay. Yeah. All right. When we solve this, we translate to the function call problem size n minus 1, num minus 1. The problem size reduced by 1. Okay? Yeah. From peg temp. Yeah, because we want to move the n minus 1 disks to temp peg. Then, after we move the largest disk, we can move it back to the destination peg. So that's why we put in the destination is the temp peg. Okay? Then the 2 peg is used as the temporary. Okay? So in that way, we solve the problem of size n minus 1 the first time. Okay? So that function call. Okay? After that function call, we need to move that disk, so we need to make one move, okay? One explicit move. Yeah. That's the not recursion step. That's the explicit move. Okay? After we make that explicit move, we need another recursion. Okay? Another recursion. This time still n minus 1 size, but the pegs we use different. Okay? Yeah. So this time we starting point temp. Yeah. Temp peg, that's our starting peg. Okay? Destination 2 peg. And from peg used as our temporary manipulation peg. You see? After that adjustment, so you can see we split the original function to 3 steps. That's the recursion. Original function into 3 steps. Okay? Yeah. So now let's write the pseudocode, the function. Yeah, that's the original function. Inside this original function, although we need to have a base case, right? Yeah. We need to assume n greater than 0. Okay. The base case, yeah. Yeah. So, all right. Okay. Yeah. Now, split n minus 1 problem, explicit move, this explicit move, okay, simulation, all right, yeah. then another n minus 1 call. Okay? Yeah. That's it. Yeah. That's the explicit move. So when you do this, because when n, think about, when n equals 0, you get out of the if statement, yeah, you reach the end of function, void, you get out of the function. Okay? Yeah. So you don't worry about n equals 0 case. Okay? n 0 case, you get out of the function. Okay. All right. So that's the function. So you can think about, to solve that general problem of size n, we just need these a few lines. We solve it. See? The problem, general size, very complicated. Very complicated. But, 3 or 4 lines. 3 or 4 lines. That's the power of recursion. That's the power of recursion. Okay? Yeah. But we pay. Think about it. The code is very simple, but when we use this method, we pay a lot. Remember the stack. Remember? In order to do recursion, we need to use deep stack in our memory. A lot of memory resource. That's the cost we need to pay. That's big cost. Okay? Yeah. So that's why, in your mind, you need to be aware of that high cost in your mind. Because here, if we do not use that recursion, we cannot solve it. So that's why we are willing to pay that high cost, because we want to solve it. Okay? Yeah. All right. Next, we need to do analysis.